All right, so welcome back. We will be still talking about electric potential today. So quickly, last time we talked about the similarity between electric potential and gravitational potential. So electric force and potential gravitational force, they are both conservative force. So in that case, the work done by electric force is decreasing the electric potential energy of the system, just like the work done by gravity decreases the system's gravitational energy. So for the change of the gravitational energy, electric potential energy in this case, so either way, so it's going to be change of potential energy du is equal to minus of the force as a vector dot product of dl as a vector. So that applies to both gravitational force and also the electric force. In the case of electric force, then the force is equal to Q times E as a vector, E as a vector. So in that case, you move Q to the other side of the equation, then changing V in differential form, we call it derivative of V equal to derivative of U over Q equals to E as a vector dot DL as a vector, okay? So then derivative of V is equal to minus of E dot DL in that case. If you are looking for the change in potential V, so V is potential, electric potential. So then is between point A and point B from point A to point B in that case. So VB minus VA equal to minus integration from point A to B, electric field dot DL, okay? So that's how you calculate electric potential difference. The electric potential energy is defined as U equal to Q times V, which we talked about in the previous lecture. So then E, you can calculate E if this is uniform field, E then equal to change of V divided by the change of the distance, which is delta S, or you can call it D, okay, for the magnitude. We talk about conservation of energy. So because electric force is a conservative force, so then the mechanical energy of the system should be conserved. Okay, so potential energy plus kinetic energy equal to constant. And then in this case, the potential energy is electric potential energy, which is Q times V. So then you can rewrite this equation. So it can be expressed in terms of kinetic energy and then the Q times the electric potentials. We talk about calculation of electric potential. So for point charge, potential is equal to KQ over R. And then when R is equal to infinity, so V equal to 0. Okay. So electric potential energy then for the point charge will be Q times V, or Q naught times V, which Q naught is a test charge. And V is equal to KQ over R, so then KQ naught V Q over R. If you have a system of multiple point charges, then you calculate electric potential by each point charge, and then you summarize them through each of the point charges. So in this case, the V is a scalar, so you just add them algebraically up. For electrostatic potential energy, so this is in case of if you have several charges surrounding each other. So there are two ways to calculate the how much energy is stored in the system. So you can imagine if first have this first charge in space, nothing is surrounding it. So then that's naturally by itself. So no work required. But then if you want to bring the second one, right? So then there's a work against that because there's electric field by the first one. So then when you bring the second one in there, so there will be work done by that. You can calculate that, and then you bring the third one comes in here, then there'll be work done to the third one by those two charges already in space. Okay, so you can calculate that way. So then for a system of three charges, you will have electric potential energy equal to KQ1, Q2 over R12 plus KQ1, Q3 over R13 and KQ2, Q3 over R23, where R12 is the distance between the first two charges, R13 is the distance between first one and third one, and then R23 is the distance between the second one and the third charge. You can also just look at QV for each of them. And in that sense, you are double counting. So then at the end, the potential energy will be 1/2 of summation of I equal to 1 through n of QIVI. Okay, so you add them up. In that case, you can also do this way. We talk about the I think that's how much we talked about last time. So this should be new for this lecture. So today we will be looking at calculating electric potential V for continuous charge distribution. So we ended at the calculating for multiple point charges. But for system of point charges, then you do summation through the electric potential by each of them. So in this case, so for continuous charge distribution, so then we can actually divide the charge distribution into small pieces, which each piece has the charge of derivative Q, right? So then instead of using Qi, so this can be treated as a particular one, a point charge in that case, right? Now, instead of doing summation, you'll be doing integration because you are dividing the continuous charge into small pieces. In that case, summation becomes integration. So then this is the universal general equation you are going to use to calculate continuous charge distribution, the electric potential by continuous charge distribution, which kind of like similar to what we did for the electric field calculation, right? For continuous charge distribution, where that is KQ over R square with the direction. But in this case, electric potential is a scalar, so there's no direction around. Now, depends on what kind of charge distribution you have. You could have one-dimensional linear charge distribution. So then dq again is equal to lambda dl. Lambda is linear charge density. Two-dimensional, that's the areal charge distribution. Then sigma times derivative of A. So area charge density times the increment of an area of derivative of A. Three-dimensional, you do rho, which is the volume charge distribution times derivative of V, increment of volume. In that case, in small increments. All right, so then depends on what you have. You are going to have dq in those three different forms. So first, we will take a look on an example of if you have line charge distribution lambda, right? So then in that case, you take a small piece from here, anywhere from here. That will be your dq. So I think you so there's an example in the textbook that is using this approach, the approach of doing DQ, okay? So you guys are encouraged to check on that one, but in the lecture here, I'll try to do this in another way. So that's and the note at the end of the example tells you the second method to do this, okay? So both ways are fine, but in the example, you have finite length of the charge distribution of length L. So then you take a small piece of the derivative L from the charge distribution, you integrate from -1/2 to +1/2. So that's one way of doing it. What if this is an infinity line charge, and then we are actually going to start from a reference point here and then ending at our point of interest P. So in this case, you'll be doing what we did earlier. So integrating through doing like E minus E dot DL and then through this path. Okay, so this could be any path. So in this case, because E we know when we talk about Gauss's law, we know how to calculate infinity line charge, right? Distribution, its electric field is 2K over lambda, 2K lambda over R. Okay, R is the distance from the line. So in that sense, so then V at P minus V a reference point initially should be minus of E as a constant here, and then DL is in this case, and then so if you do dot of R in that direction, that gives you its component in that direction. So then dr. Okay, so integration from lower limits to upper limits. So that means R sub reference to R sub P. Okay, so this will give you natural logarithm of R, and as a result, it will give you this answer. Okay, it looks a little bit different from the example in the textbook, but this is because this is in infinity line charge, but in the problem, there's limited charge of length L. Okay, if you take L to the infinity, then it will be giving you the same result as this guy. Okay, all right. Let's take a look on if this line charge is a ring. Okay. So if you have a ring, then you are going to take dq as a portion, small portion from the ring, and this ring has a radius of a, and then you are at point P, which is at the exit going through the center of the ring, perpendicular to the surface of the ring in that direction. That distance is z. Okay, so by this small amount of dq at this point of P, you should have v or delta of v, okay, equal to kq, k dq over r, and then integrate through the whole thing will give you the v, okay? So dq here will be the line charge distribution, okay? If you have total capital Q there, then lambda will be equal to lambda will be equal to the total Q divided by 2 pi times A, okay? But if you take this as dq, you can integrate through the whole charge, right? So then just take a dq as an integral and as the variable here. So everything else is not dependent on the dq, okay? So you are going integrating through the whole thing. So that means it gives a result of Q total charge Q. So KQ over R, okay? So R will be the distance. And R you can calculate by Pythagorean theorem, A squared over Z plus Z square root of that to get R. So we can expand this result into a spherical charge distribution. In this case, if you have a disk, right? So then you make a small ring out of the disk that is concentric to the disk with the radius of A. And in this case, A will be the variable. A can increase by small amount of derivative of A. So in that case, then electric field by this small ring at this point P will be equal to dV. Okay, dV then will be what we get from the previous K of Q, total Q. In this case, it will be the Q from the ring because now the charge on the ring is dQ. Okay, and then you can calculate using the aerial charge density. So it will be sigma times area. Area of this ring will be 2 pi A, right, times this derivative of A. Okay, so this is the sigma, this is area, derivative of area. Okay, and then over the R will be square root of A squared plus Z squared. So you integrate through when A equal to 0 up to the radius of the disk from 0 to R. Okay, and looking at this integration, so sigma k 2 pi, they are constant numbers, they can go out of the integral. ADA over square root of Z squared plus A squared, that gives you square root of Z squared plus R, okay? And then taking Z squared plus A actually. And then taking the limits are from 0 to R, okay? So then that gives you this result over there, okay? So the integration. All right, so this is for surface charge distribution. Now for volume charge distribution, we will look at the simple case of the spherical charge distribution and then uniform charge distribution in this case. So if you are outside of the charge distribution, then E at any point, you can use Gauss's law. It's easy to determine E is equal to KQ over R squared when in the radial direction of R prime, where Q will be the total charge on the surface, on the spherical charge distribution. And derivative of V equal to minus E dot dl, okay? So E is in the radial direction, so this is E, and then dl, okay? So dl will be, that will be any like derivative of L in the radial direction, so that will be derivative of R. So then integrate through from infinity being 0 of your electric potential to any point here. Okay, so you're integrating actually from infinity to any point of your interest here. So in that case, you integrate through this guy, right? So from infinity to R prime. So then the result, because there's a minus of 1 over R squared, KQs are constants. Okay, so then result will be 1 over R. All right. So from infinity to r prime. Okay. So then if r equal to infinity, the second term will be equal to 0. So the upper limit goes in here, becomes kq over r. Okay. So this is the integral we can use. Inside the shell, so if this is a shell, okay, so this is a metal sphere. Because it's a metal sphere, so it's conducting, so then charge will be on just on the surface. So inside the conductor, we know electric field is equal to 0, okay, because that's one of the properties of conductors. So then there will be no change of the electric potential. So inside that will be the same as just on the surface. Just on the surface, it will be kq over capital R, because that's the distance from the center of the sphere. Okay, that's that guy. So then it's going to be constant. So it increases from 0 to kq over R, and then now stays the same throughout. Okay, the conductor. All right. Let's take a look on the first example here. It says a metallic sphere of radius 2.0 meters. So inside here, this is a metallic sphere. So again, because it's metallic, so it's conductor. So then the charge will be just residing on the surface of this sphere, okay? Uniformly charged to 5.0 micro coulomb and stands on an insulated stand surrounded by a larger metallic sphere. So this, the second one outside here is also metallic sphere, spherical shell. Inner diameter is 5, outer diameter is 6. And uniformly charged with -5, okay, microcoulomb. So the -5 should be just on the outer surface, okay, because this is a metallic shell, so it's conductor. Well, actually it's inner. It will be inner because positive is here, so this guy then will be on the inner surface, not the outer surface. So it says if the potential is 0 at infinity, what's the potential at the shells, the spherical shell, and the inner shell? So that means this is the outer shell, and then inner shell over here. And what will be the potential and the space in between, and then inside the shell here, and outside the shell. All right. So let's take a look on this one. So there's a positive charge sphere, and then there's a shell, negative charges on the inner surface, okay, and then 0 on the outer surface. So we know E equal to 0 at infinity, right? And R equal to infinity. And also V will be equal to 0 at R equal to infinity, okay? So the electric charge. And because there's a plus 5 microcoulomb here, there's a negative 5 microcoulomb here, right? So then outside the shell, we should expect electric field equal to 0, right? Because if you draw a Gaussian surface, right, and then plus 5 and minus 5 will cancel out, become 0. So then E times A is equal to 0, right, over epsilon naught, which is 0. So then E will be 0 outside the shell, okay? So if that's the case, then the potential outside the shell on the outer surface, right, will be the same as when the potential is equal to 0 at infinity, because V equals to E dot dl, right? Integration from infinity to your point of interest. If this guy is 0, then it's going to be 0, no change, right? So the change in potential is 0. So then V equal to V infinity equal to 0, okay? For the first question asked. So then at the spherical shell, that's going to be 0. And at the inner shell, it's also going to be 0. Oh, actually, sorry about it. So I think so this is the spherical shell over here. And then the inner sphere, okay. So it's talking about inner sphere over here. So we should calculate, not this guy. But yeah, so this one is asking at this point for B, and C will be space in between here. Okay, R equal to 2 to R equal to 5. And then inside the sphere will be R less than 2. Okay, and then outside the shell. So outside the shell, okay, outside the shell should be equal to 0, right? That's something here. Okay. So as it goes to this point, right? So be 0 and then going through and then until it hits this. So A and E are both 0. Okay. For part A and E. Okay. Now let's look at B for part B. So this, if this is 0 and then this is conductor, so it should be 0, right? Up to this point. So then in between, so I think we can calculate, or you can look at the scenario in between first. Okay, in between, you draw a Gaussian surface, right? So then that Gaussian surface, you have this same magnitude E times A, that should be equal to Q enclosed divided by epsilon naught, right? So E would be the constant you're looking for, and then 4 pi R square, right? The Gaussian surface. Q enclosed then will be the charged by this inner sphere, okay, which is positive 5 microcoulomb over epsilon naught, okay. So E then equals to in this case it will be let me just call it this like Q enclosed over 4 pi epsilon naught times R square, okay. 1 over, so this could be like KQ enclosed over R square, right? Because 1 over 4 pi epsilon naught is K. All right. So then for delta V, it's going to be from where R equal to 5 centimeter, right? To any point. So if we are looking on this guy, so then the R equal to 2. Okay, so this is what we'll be doing. And minus E dot DL, okay, where this is going to be, so minus goes in front, 2.0 meters and 5.0 meters, okay. And K, so you take this one in here, and then that one will be like dr times dr, okay. So that gives you like KQ enclosed over R square dr. All right, so the result will be, so this will give you KQ enclosed over R, and then from 5 to 2, okay. So we can plug in the number, so 8.99 times 10 to the, oops, out of paper. That times Q enclosed will be 5.0 times 10 to the minus 6. That's in coulombs, right? And then times 1 over R equal to 2, which is 2.0 times 10 to the minus 2, because that's 2 centimeter, minus 1 over 5.0 times 10 to the minus 2. Okay, and then do that. So 2.0 times 10 to the minus 2 minus 1 over 5.0 times 10 to the minus 2. Okay, so this gives you delta V, the change in potential from 5 to 2 to be equal to about 1.35 times 10 to the 6 volts. Okay, and because when V at R equal to 5 centimeter, that's equal to 0. So then V at R equal to 2 will be adding this up, right? So it's the 1.35 times 10 to the 6 volts. Okay, so that's on that one. So part B, part C is asking you the space between the two. So space between the two then is similar to this guy, but your integration here for the change of delta V should be it just goes from R equal to phi to any particular R that is in between phi and 2. So it's greater than phi, but less than 2 centimeter, or greater than 2 centimeter, but less than 5 centimeter. Okay. Minus E derivative of L. So there'll be minus the same thing, whatever we have there. But so I'm not going to repeat that, but this is going to be equal to minus, or actually it's going to be K Q enclosed, okay, over R, and then over R, and then from R equal to 5 centimeter to R. So this would be K Q enclosed times 1 over R minus 1 over 5 centimeter, okay, in that case. So I think this would be just an expression, and then you can take in the numbers here, 8.99, and this guy will be the 5.0 micro, 10 to the minus 6, okay? So for that one. For D, inside the sphere, so inside the sphere, because it's a sphere, right? So then it will be the same as just on the sphere, which is this one here, okay? So V will be the same when I less than 2.0 centimeter, will be the same as V I equal to 2.0 centimeter. That is 1.35 times 10 to the 6 volts. Okay. And for E, we already had that in pi already. That should be also equal to 0. Okay. So that's on this one. So there are different scenarios involved. Let's see if I can capture everything in one shot, on one screen. Okay, it's a little bit hard, but somewhere there. Okay. So let's go back to the PowerPoint slide. So I think we have mentioned this in the previous example. So if you have a spherical shell of charge, okay, so then E outside of the shell, that is KQ over R squared times R in the radial direction, derivative of voltage will be minus E dot dl, and then E is in that direction, so this guy will be giving you dr, so KQ over R squared dr. So integration then from minus of E dot dl, that's where the minus sign goes, is equal to KQ over R, okay? So the electric field inside the shell will be 0, so then the potential will not change. It will be the same as on the surface, okay, which we have looked at in the previous example. Okay, so let's take a look on this example here. It says a metal sphere centered at the origin of a surface charge density that has a magnitude of 24.6 nanocoulombs per centimeter square and a radius of less than 2 meters. So it's an unknown. A distance of 2 meters from the origin, the electric field is 500 volts, and the electric field strength is 250 volts per meter. It's asking you what's the radius of the metal sphere and what's the sign of the charge on the sphere. Explain your answer. Okay. So for a metal sphere, if you're outside the metal sphere, so it says it's less than 2, right? So you're outside the metal sphere. So its electric potential then is similar to a point charge of V is equal to KQ over R, okay? So in this case, so then this is what we have if you're outside the sphere, okay? And then if you're inside the sphere, we know that, so this is for R greater than R, but V is equal to KQ over r. R will be the radius of the sphere for r less or equal to r. So on the surface of the sphere or on surface or inside the sphere. Okay. So there are these two scenarios. So it tells us that radius less than 2, but it tells us the potential at 2, right? So that means there's this condition. So you have this as the 500 volts. And K is a constant. Q you can calculate because it gives you the surface charge density sigma. So Q you can calculate is equal to surface density charge density times the area of surface, which is 4 pi r squared for the sphere, right? But in this case, you should use the radius of the sphere instead of the distance r. Okay, so we are looking for the r, the radius of the metal sphere. So this guy is equal to 2. Okay, so 500 volts is equal to 8.99 times 10 to the 9. Okay, with the correct units, this is SI unit, and times this together, sigma is 24.6 10 to the minus 9. Okay, coulombs over meter square times 4 pi times r square. Okay, and then divided by 2.0 for that small r, but let's not use any units for right now because everything is in SI unit. So you can solve for your r. Okay, so on this equation, you solve for your r. It turns out to be 0.66 meters. Okay, for this r. All right. And now it's saying what's the sign of the charge on the sphere. Okay, so the charge of the sphere. Now, because V that is equal to KQ over R, right? So it looks like, and V is positive. So that looks like the Q is going to be positive. Okay, so then that's positive, right? So we actually don't end up with using the 250 for the electric field. Okay, so we can just solve the problem using the voltage here. But you can also use the electric field. I think you can do that. So E field is KQ over R square. Okay, so from the equation, you should be able to get the same answer. Unless the two numbers, 500 volts and 250 are contradict to each other. Okay. All right. So going back to the PowerPoint slide. So we know we can calculate the differential derivative of voltage equal to minus E dot dl. Okay, and then that's E cosine of dl. So if V depends on only in X, right? So dl could be in 3-dimensional. Now, if you just focus on 1-dimensional, then that's purely in X direction. So then this dl becomes dx. Okay, so it becomes dx. So you can see dv in the x direction is minus E dot dl, which is minus E dot dx in the I direction. Okay, and if E is in the I direction, so that becomes 1. Okay, so E, the x component of it, because this is E dot I in the I direction, that means the x component of it, right? E sub x, so this should be E sub x times dx instead of E times x. So then you can see E sub x, the x component of electric field will be minus of derivative of V x over dx. Okay, so then you can calculate for the x component of electric field by derivative of Vx times dx and minus sign. The same will be applying to the y component and z component. So E of y component should be minus derivative of Vy over dx dy, okay, or V as a function of y over dy. So this means V as a function of x, and then EZ component will be minus dV as a function of Z over dx. Okay. So then the 3 components of electric field can be doing derivatives of with respect to x and y and z. So now we have 3 variables as derivatives here involved. So in that case, if they all appear together, then you can only write them as partial derivative because there are 3 variables, but you are doing derivative only to one of them. So that's called partial derivative. So then E of x becomes minus this sign for partial derivative of v over partial derivative of x is the same operation if you would have do for derivative, okay? Just the same as derivative of v over derivative of x. Ey will be minus derivative of y, partial derivative of y, and then partial derivative of v over partial derivative of y. Ez will be minus partial derivative of v over partial derivative of z. In that case, you give this, you have this example, you have the operations for each of them, x, y, and z components, okay? And then you get the, this will be the x component, all right? And y component and z component. So by doing that, so this operation of doing partial derivative of the quantity to each of x, y, and z is called gradients, or symbol as the upside down triangle with the arrow on top, because it gives you a vector. Okay, so then this operation actually results in a vector, which is the electric field. Okay, so this is in the Cartesian coordinates. In cylindrical coordinates, then it becomes a little bit different when you do gradient. So there's a the radial direction partial derivative over r, but in the this angular direction phi, and then this will be 1 over that 1 over r radius partial over partial the phi, and in the azimuthal direction partial over partial z in the z direction. In spherical, it changes to this guy. Okay. All right. So let's take a look on the example here. I think we are going to just mainly dealing with the Cartesian coordinates in this class, okay? And then you guys might do this in an advanced class later, like these two, okay? So in this case, it says in a particular region, the electric potential is given as a function of V, that is x, y, and z function, right? So minus x, y squared z plus 4xy. What's the electric field in this region? So you're doing gradients for this guy, okay? So that means you are doing partial derivative of v over x, and then partial derivative of v over y, and then partial derivative of v over z, and with the minus sign, okay? All right. So in this case, your E as a vector is going to be minus derivative of gradients of your V. This is scalar, so this is a gradient. So there'll be minus of partial V over partial X in the I direction plus partial V, partial Y in the J direction plus partial V, partial Z in the K direction. And then V equals to minus X, Y squared Z plus 4XY. So partial V over X, so that's minus YZ squared plus 4Y. Okay, so minus the first one, minus Y squared Z plus 4Y in the I direction. The second one, partial V, partial Y, so that gives you minus X, Y squared becomes 2Y, so 2XYZ plus 4X in the J direction plus partial V, partial Z, so then it will be minus X, Y squared only. This guy, the second term does not have Z, so it's 0, K direction. Okay. Putting the minus into the square parentheses, so the first term becomes Y squared Z minus 4Y by I direction. This becomes 2XYZ minus 4X J direction, and then that becomes positive in K direction. Okay, so this would be your E field, okay? XYZ direction. All right, so let's go back to the slide. So now let's go back to the equipotential topic. In this case, I think we talked about the equipotential lines. So now equipotential surface. Okay, so this is similar to the contour map. So when you have the contour map, we know that where you have the equipotential line, right? So at any of those, they are equipotential line. Okay. So similarly here for equipotential surface of uniform electric field, in this case, the two plates, right? So you can expect this is a surface. If you do that way, cut in that direction, right? Give you a surface in that direction. So then those dashed lines are the equipotential surface, okay, or equipotential surface, okay? And if you have a not uniform field, so in this case by a spherical charge distribution, so those circular, or this is could be think about like cross-sectional area. So you just think about the spherical surface of these ones. On them, you will have equipotential surface, right? So if on the equipotential surface, you should have potential equal to each other. So that means derivative of potential equal to 0. So then minus E dot dl equal to 0. So that means the normal direction and the E field are perpendicular to each other, or E field is in the normal direction of that surface. Okay, so minus E dot dl should be equal to 0. So the result will be then equipotential surface or line should be perpendicular to the electric field. Okay. And then for point charges, this is what you would expect. Okay, so for positive charges, in the middle, you have no electric field, so no electric field lines, but equipotential lines or equipotential surfaces look like something like the green lines, okay? And then on this case, green lines and yellow lines are the equipotential surface. If you have two charge conductors connected by a wire, conducting wire, so because that conductors connected, so the potentials on those surfaces should be the same. Now the charges on them, so it will be different, but we should talk about like the charge densities on these two surfaces. Okay, so because the potentials are the same, so then by a spherical charge distribution, you have KQ over R1, and then this guy will be KQ2 over R2. Okay, so Q1 and Q2 can be calculated using the surface charge density times the area. So sigma 4 pi R square. Q1 will be sigma 1 4 pi R1 square, and then Q2 will be sigma 1 4 pi Q2 square, okay? R2 square. And then plug into this equation, so then you get just K sigma 4 pi R on the left-hand side, K sigma 1 4 pi R1 square, right? Divide by R1, so R1 and square will cancel. And K will cancel, 4 pi and 4 pi cancel. So at the end, you should just have sigma 1 times R1 equal to sigma 2 times R2. So the result then, it shows these two are the same, right? Sigma 1 R1 and sigma 2 R2 are the same. So then if R1 is greater, that means sigma 1 will be smaller. Okay, so if you have larger radius, you have smaller charge density. And then if you have smaller radius, you have larger charge density. So the conclusion is that if you have surface charge density, if this is a continuous charge of conductor in a sense, because the charges on conductor on the surface. So at the area that is sharper, you actually would have larger charge density, and then the area that has not as sharp. Okay, so it's the like more flat area. Okay, so in that sense. And so this will be another scenario. But on the surface of this conductor, if this is conductor have irregular shape, somewhere is sharper, somewhere is not as more flat. So then you have more charges on that tip. So then the electric field will be more stronger there on the surface of the conductor because it's an equipotential surface. So then the lines should be perpendicular to that surface. Okay. All right. Moving on, applications of electrostatics. So you know of Van de Graaff generator, which used to generate large charge accumulation over the sphere, and then that can be used for experiment in that sense. So basically you rub the rubber belt with this metal, which is connected to the ground. So then positive charge and negative charge will be generated on the metal and then on the belt. So as the belt is running through there in contact with this guy, the positive charge will be building up there. The charges on this guy will be dissipated into the ground. Okay, so at the end you got this accumulation of a lot of charge there that can be used. And electrostatic is using also in Xerox, so that's how they are charged, and then tuners can be deposited to the paper in that sense. Okay, to create the images. Laser printing is the same thing. So the inks are charged, and then there's an electric field in there. So then you can bring the printing to any specific point you want. Okay. So another illustration of that. Okay. So electric field, charged electrodes, and the inks being here. So project to the specific location on the paper for printing. Electrostatic precipitator, so which works the way that the molecules flow through here. The first one, you have neutral particles and then get charged, get trapped in that sense, and then the final, when they're out, the particles will be trapped over there. So then you have clean flow of air comes out in that sense. Okay. All right, I think we will stop here for today, and then we'll come back next time. Mainly we'll be focusing on electricity and circuits. Bye, guys.